Hello and welcome, and thank you for joining us today. I'm your host, Leila, and welcome to the webinar, What's New in Fatigue Durability? Fatigue and Durability Explained, sorry. So before we begin the presentation, I would like to review a few housekeeping items with you. So please take a moment to observe the tools available in the WebEx event window in case you have any issues. Question may be entered in the Q&A panel at any time. A technical team services is available live to the Q&A panel answer any question you have durability today presentation. An answered question will be addressed and dedicated from the Q&A section at the end of the presentation. For technical support or other questions, please contact us using the chat function. The webinar is being recorded and will be available later for you. I would like now to welcome Nicolas Baron to begin the presentation. Thank you.
Thank you, Leila, and welcome everybody to this seminar. Today's talk is going to be about fatigue and durability. So if you're new to this field, you are at the right place. I hope you will enjoy today's seminar that will last roughly 3 hours. So that's quite a long time, but I think there's a lot to cover, and 3 hours is really the perfect amount of time. We have a 10-minute comfort break right in the middle of the seminar, just in the middle of the seminar roughly, so that you are more comfortable watching this seminar. Okay, so let's start. Why are we here this morning? What is the purpose of this seminar? Why are you attending today's seminar? The purpose of this seminar is to teach you the practical fundamentals of fatigue analysis. So we're not going to really have a technical expert session. That's not the goal today. The goal is really to introduce you to the ideas the foundations of fatigue and durability. We also cover some typical applications of fatigue life prediction during this seminar. It's a very hands-on, very approach seminar today. Really, theory will be limited to a bare minimum today. What are we going to learn today all together? A couple of things. First, we will review the definition of fatigue and the physics behind fatigue. So what's the reason for fatigue, and how can we describe fatigue? What are the physical explanations that lead to failures by fatigue? We'll see what drives fatigue and crack growth. Crack growth is it's the first time I'm using that word today. We'll not cover crack growth so much today. We'll mainly cover two other routes for fatigue analysis. But crack growth, we'll mention it in passing, giving some explanations. So we'll see what drives fatigue and crack growth. Third point, we'll look at the various common methods there were for analyzing fatigue performance. There were a couple of ways, a couple of routes we could use to analyze our fatigue designs. We'll highlight the very common, the very typical ways we can do in real life. And practical configurations in fatigue analysis will be mentioned also along this seminar. And as I said, we're not going to prove how to memorize equations. So math and the equations really that are behind fatigue are not in today's scope. That's very interesting, I'm sure, but today we really want to be focused on the practical view on what drives fatigue and what is responsible for fatigue failures. All right. I hope you are quite excited by this agenda. So first, let's see why is it really important to study durability and to study fatigue. I think we have a nice illustration here of this helicopter here. It's submitted, the passenger is submitted to various aerodynamics cyclic loads here, and for sure, if this is not studied properly, you might have trouble. This helicopter blades here could fail if not studied properly. So there is some aerodynamic turbulence and loading here, cyclic loadings that could potentially result in fatigue fractures. Also, typical electronic components could be submitted to cyclic loading. Think of a computer that's carried over when you travel and to work, to home, and there are a lot of loads imparted on that electronics device. So that it's also important to cover that kind of loading for an electronic device. Structural components also typically are exposed to cyclic loadings. That's important to understand the sources of these loads here. Which are the ways through which the loading will import the component and will reach our component. Can we characterize these loads? What are they like? Are they do they bear some high peaks? Or are they rather constant? Which are the really what do they contain, and what in what ways their content will have some consequences in the way our item can withstand fatigue or not. That's very important. How can we characterize our cyclic loadings? And the results of these cyclic loadings, we'll see, could be typically fatigue fracture. One word that you see along all these items here, probably you've noticed if you're observant this morning, it's cyclic loads here. You see it's coming for each and every item here, we have the word cyclic loadings. And this is a key thing here. Cyclic loading is really what drives fatigue. So whenever we are talking about fatigue phenomena, we have cycles involved. We'll cover that at great length in the coming minutes. But first and foremost, it's very important that you have this very clearly set in your mind for today's seminar. Cyclic loading is really necessary for fatigue phenomena to occur in our items. This is a key thing in fatigue. There must be some cyclic loading, otherwise there is no fatigue failure. There might be failures, but in case there's no cyclic loading, these failures are not considered fatigue-induced failures. So why are we here today, and why are we spending some time and your time studying fatigue? It's very important to recall that in the real world, and this study is from it dates back now to 1982. That's quite many years back, but it's still most probably it's still valid today. And what do we see here? We see that around 80 to 80% of all structural failures occur through a fatigue mechanism. That's massive, right? Just 80 to 90 of all structural failures are due to fatigue. I think that's very impressive, and that really emphasizes the need for characterizing fatigue in a proper way, so that as designers we are then able to fight against those fatigue failures and can design in a way that's really robust and reliable, robust, and that allows our items to behave as we expect them to behave in the field, in the hands of our customers. So in terms of money here, since this is a massive 80 to 80% of fatigue failure or failures occurring because of fatigue, we see that it costs a lot of money. In the US here, it was estimated an annual cost of $1.5 billion due to fatigue failures. I think that's a big number here, and that really shows how much money, how much is spent due for fatigue, for failures due to fatigue, and why we shall study them really carefully, so that this money is saved and it is not spent fighting against those failures. And we estimate here that the cost, this $1.5 billion, again, that's such a high number, could be reduced by 29 to around 30% by application of current fatigue technology. So you can save a lot of money if you understand fatigue better or well, and you can save your company, your organizations a lot of money. Not only money, but also think of the consequences there would be in terms of reputation for the organization, when many items would fail in the field while used by our end user customers due to fatigue. So not only cost, here we highlighted cost, but as important as cost comes your organization's reputation, which is key today for you to continue selling your products. So we are here, of course, because fatigue in itself is an interesting phenomenon to study, but not only for that. And the main reason we are here today is because this topic is addressing failures that could result in massive spendings for your for your organization. So there's a lot involved here. The stakes are very high. That's really the main motivation for us being here today with you. Finally, we could just have a way and look back in the past. Here, anyone who lacks, look at this quote here, I like it. Anyone who lacks knowledge of fatigue can double or triple design factors and formulate a design that will not fail. So there is the idea of safety factor here, safety, a margin of security. So of course, even if you would not know anything about fatigue, you could design your products in a way that will make for this little knowledge, and you could increase the size of your designs, have material choice that make it so that most probably it will not fail. That would be an option, and probably that used to be an option decades ago. That is no longer the case nowadays. Such designs nowadays, they cannot compete in the marketplace. We are in a very competitive workplace. We really strive. Really should strive for creating products that really address their end markets in a finely tuned way. We cannot just make our design very bold so that we are sure we will not face any problem. We have to be better. We have to improve on that. We have to build on the knowledge we have accumulated over the years in the field of fatigue so that we can employ this knowledge to our advantage in creating products that really will be finely designed, finely tuned, so that engineers are really doing their best and using the knowledge, their all the fields, everything they know about fatigue. So we can improve our design. That's my main point here. We can not just continue creating design in product as we used 50 or 60 years ago, but now we have a lot of new knowledge. We have computers, we've got software, and we're going to demonstrate that today. How can we use a software package to assess the effect of fatigue? So today we can do better than what engineers used to do 100 years ago, and we shall do that. Let's continue just as an illustration to showcase the relative importance of different phenomena making responsible for failures. You see on the left side here, we have a list here of different failure modes that could result in failures. And you see that on the first two here on the top here, the first two lines here, are the main ones, meaning corrosion and fatigue are by far the two reasons, the two failure modes rather, that lead to fatigue failures. So we must study those very carefully. Corrosion, I'm afraid there is not much we can do about choosing the right material. Apart from that, I think there is little we can do. However, as regards fatigue, there is for sure a lot we can do as engineers to design our products so that they can withstand the loads, the cyclic loads they will be subjected to in real life. And we see here we have two pies here. The one here to the left is for general engineering components. We see that fatigue response is responsible for roughly a quarter of the failures. So that's about 25% or a quarter due to fatigue. That's quite much, and I think that's already enough to justify why we should, as engineers, have a solid foundation, a sound foundation in fatigue phenomena. But look at this on the right side. It's even more astonishing here, more impressive. If we focus on aircraft components solely, we see that 55% of the failure modes are fatigue. I think that's so much. That's very impressive. And for sure, engineers working in the aeronautical business, aeronautical field, for sure they have solutions to study fatigue. I mean, it would just not be possible otherwise. Thinking of this 55% failures due to fatigue, that's so impressive. So here, that was just motivation to illustrate why it's important to study fatigue phenomena, fatigue failures, why it's important to understand them so we can mitigate those failures and we can fight against those while designing. Okay, so that was mainly just an introduction as for today's seminar. That's motivation for why we are here today. Along the course of this seminar, we'll, as I said earlier, we're going to describe fatigue phenomena, what it's due to, what are the roots leading to fatigue, and also we're going to use some software tool, typically ENCODE, of course. This is a seminar hosted by HBK. So we're going to introduce the ENCODE software tool to help us evaluate and calculate some fatigue results. Here we have an illustration of design that's been calculated. It's a numerical simulation, as you can see here. So we'll see which are the packages available within the ENCODE software tool that can help us calculate the fatigue result of this control arm, this bracket here. You see here on the right side, this is the result in terms of fatigue here. You see on the right side, there's a life in terms of number of repetitions of the input signals that lead to fatigue. That's the final result we are after. And so here we have a real signal here. That's the real loading we're measuring. And the software brings some boxes, some glyphs, we call them, that encapsulate all the knowledge needed to be able to calculate fatigue results. So here, some minutes of this seminar will be dedicated to understand what's going on here and how we can finally get the results in terms of fatigue here, and which are the best practices you should follow as engineers when wanting to calculate some fatigue results with the numerical simulation model. Before we really do that, before we enter in our main topics, let me take the opportunity to introduce our company. HBK Prentia. Prentia is a software arm of HBK, Oettinger Brill and Care. Within Prentia, we've got two main brands. As you see on the right side here, we have ENCODE and RelySoft. These are the two software brands that are part of the Prentia family. They address different needs. We'll talk about that in a second. So in terms of software, again, we have RelySoft for reliability challenges, reliability calculations. Typically, when you Weibull analysis, maybe you've heard that term before, it's not fatigue, it's something a bit different. It's reliability, and it's the reliability topic here. So it's somehow connected to fatigue. It's kind of a superset of fatigue. Well, just to say, just to make it simple this morning, we're not going to study anything related to reliability, but reliability really comes very well together. It's a companion side of durability. So having the two software brands within the same company totally makes sense. So this morning, today, we're not going to focus on reliability, which is covered by RelySoft, and you can do things like live data analysis. You can even create accelerated live testing analysis. If you're interested in that, really get in touch with us. It's such an interesting topic here. You can create testing tests in a way that accelerates the failure, so that you are able to design in a faster iterative loop, so you can develop faster. And we know today it's key to be able to put products on the market as soon as possible. So system reliability, maintainability, maintenance things, what I do to optimize my maintenance schedule in my factory, all these things can be covered by RelySoft, which we're not going to cover again today. Today we're really going to cover somehow digital signal processing. Fatigue involves some digital signal processing, and we're going to talk about strain gauges, not only strain gauges are the result of physical measurements, but also we're going to touch briefly about fatigue calculation based on finite element modeling, and that's FE-based fatigue analysis. That's that's permitted through ENCODE. With ENCODE, we can analyze things both from strain gauges measured in the field, and also we can calculate fatigue results based on numerical model. We'll cover that. I'll come to that towards the end of the seminar. And finally, we provide some trainings. Really, we have many trainings, physical, in person, but also online. And chances are there might be a training you might want to consider if you want to further deepen your knowledge in some of the topics that Prentia and ENCODE or RelySoft are experts in. So have a look at our website, where you will find all the trainings available. And finally, there are also some services we provide. You might need to have some of our experts coming to your field to investigate some specific cases, some challenge you're facing and you can't find easily answer to. Probably there are people within HBK that could help you in doing so. All right. Oh, okay. So, okay. So in terms of software names, as I said, we have within Princer, there is Encode, which today we're going to talk exclusively about, and there is Realisoft. So Realisoft, just in a couple of words, and that will be the final words from me on Realisoft today. Realisoft is a big software package. It's a really complete suite for reliability analysis. It comes with software packages dedicated to many of the aspects that are concerned with reliability calculation. Very well known Weibull++, used by thousands of companies worldwide, that addresses live data analysis. When you've got time to failures and you want to calculate statistical distributions and make predictions, that's Weibull++. You have Blockchain when it comes to system analysis, Lambda Predict when you don't have figures, you want to use some international standards to predict things when starting the design, and more. There is even more in Realisoft. XFMEA for doing failure mode and effect analysis. Well, you see, there's a lot in Realisoft. If you're interested, please get in touch with us. Today, we are mainly going to focus on Encode, as I said, and typically on Glyphworks and Design Life. Vibesys is dedicated towards vibration and acoustics with analysis really that address the specific needs of the vibration and acoustical world. Akira is a new software tool we have. It's a web-based browser that allows you to access all your analysis very simply on a server, so it's very powerful. But today we're not going to talk about those. Really, Glyphworks and Design Life are going to be our main interest this morning. So the agenda, what are we going to cover? I'll start with an introduction to fatigue. There might be some newcomers to this seminar, so it's obvious that it's very fair that we shall start with introducing what fatigue is about. We'll then move on an overview of the fatigue analysis techniques and routes you can take to analyze your design. Specifically, we'll focus on the two main strategies, three main routes there are to study fatigue, which are on the one hand the stress life method, also sometimes called simply SN. S stands for stress here, and we're going to see later what this means. If you're new to fatigue, probably you have no idea. It will be very clear in a minute. And the second methodology is called the strain life method. So this time we've got the E here for deformation, so strain. And again, we're going to unveil in a second what this means. We are then going to see some practical examples of doing some calculation with the software, making use of strain gauge measurements. And finally, we'll conclude the seminar with an example of fatigue calculation through Design Life. That's our software dedicated to calculating fatigue results when you have a numerical model at your disposal. And today, most companies, if not all, do some numerical calculation, numerical modeling before creating their product. So having the option, the possibility to calculate fatigue things without even having any prototype becomes very key in designing quickly things and put them on the market very quickly. So this is the agenda for today. Let's start with the introduction to fatigue. Let's define what is fatigue really, because it's very important to be accurate as much as possible when we define physical phenomena, physical ideas. Fatigue could be very loosely defined. Let's try and be accurate as much as possible. Then this will really foster a better understanding of what are the tools at your disposal to fight against fatigue failures. So fatigue. What is fatigue? Simply look in the dictionary and you will have some kind of definition such as this one, but it's very important to be accurate here. So what is fatigue? It's the weakness in metal or other materials. So you're not limited to metals. Very often in the field, practically we're studying metals, but you're not limited to metals really. It could be any kind of material. So it's the weakness in metal or other materials caused by repeated variation of stress. Hence the word cyclic loading that we used in the introductory slides. Remember when I said, what do you see here on all these bullet points, what do they have in common? And I said, there is the word cyclic loading. And this is the reason here, because by definition, fatigue is created by a repetition of varying stress in your design. So you need variation, you need two things. You need variation of stress on the one hand, and you need to repeat those variations across with time. So we have two stages or two steps here. We first have the initiation, that's one, and second, we got the growth of a crack. So we start the fatigue fracture with a small crack, and then this crack will start growing, will start expanding. So we assume here that there is an already existing defect, so it's a pre-existing defect, and this defect might or might not, it depends, expand, grows until it reaches a critical size, and then the critical size of this defect would then lead to a total fracture of your component. So just to reiterate here, because this is very important, and I think if there is one key message you must take away from today's seminar, if you're a beginner, it is the fact that fatigue cracks are caused by cyclic loading. So we really want a variation of the stress acting on our design. So that's one thing, having this variation of stress. Second, another important thing is that the part, as outlined here, can fail even though the stress values are not really high, and that's key in fatigue also. You don't need a big load, a big impact, a big force to create the fracture. Fatigue is not about that at all. Fatigue is really the repetition of cycles at maybe a rather low value, but it's the repetition that will create the fatigue. So that is the definition of fatigue. I hope it's clear. It's variation in stress in your design, and these variations of stress must be repeated over times. That's why we call them cycles of loading, and these cycles of loading might or might not, depending on various things, which we'll cover in the coming minutes, might or might not result in fracture, in breaking. So that was for defining fatigue. Two main failure modes. The first one is when you have a big loading at once. You just import a very strong force, for example, on your design. And that's what we call static failure here. But that's not really fatigue. As I said before, fatigue doesn't really need a high force. Here, when you have a high force, such as this one here, you might exceed the tensile strength. So you are just imparting a very high value force or acceleration or whatever the loading is to your component, so that in one go there you reach breakage. So the failure really occurs immediately, so to speak. So in one go, that's static failure, and that is not fatigue failure. Fatigue failure, on the contrary, occurs really after a period of time, after this high number of cycles I was referring to will manifest itself. And this can be the case even in the situation where a low value of stress is applied to your design. So here on the chart at the bottom here, we see a graph showing the stress value evolving over time. And that's good because, as I said, we want variation in stresses, right, in our component. So the fact that stress is varying is a good thing. Well, it's a good thing. It's a thing of life. It's not a good thing in such, but it's what happens in real life. It's a good thing. I intend it could lead to failure, to fatigue failure, and that's what we're going to study today. So for us, it's interesting. That's what I'm meaning here. So stress is varying over time, and that could result in fatigue here. The point here is that the stress value, the maximum stress value that you see here, might never exceed the tensile strength. It might be a very low value, rather low value, but each of these during each and every of these cycles, the cycles we will describe what they mean later. But during the repetition, during the time application of this stress here, there will be some fatigue important in our design. So finally, the component, as we say here, gets tired, and that's really the name fatigue. Just as we human beings are getting tired after a repetition of things we're doing repeatedly, it's just the same thing for mechanical components, for engineering design, engineering items. They get fatigued, just as we human beings. When you repeat things on them, when you import them, loadings at a repeating varying load, they will have this fatigue behavior, and finally, for them, it means they break. But the analogy with human beings is just there. It stands. That's why it was called fatigue in the first place. So let's elaborate a little bit on this cyclic fatigue loading I was referring to. Constant stress, as said here, will not cause crack initiation or growth. So imagine you would have a constant value, constant stress application. That would not be fatigue. I'm repeating this, this today, and maybe it's a bit annoying for you, but I'm repeating that. But I think it's important so that everyone really gets this message very clear. We need the stress to vary, and here we have an example of something that resembles very much a sinus wave here, where the stress varies from a maximum value S max to the value of a minimal value S min here. So here it's the change in stress going from S max down to S min here. So changing the value of stress that will result in fatigue. And specifically, really, what is important here is this variation here. How big is that variation of stress in my component? So the variation, typically we define it through the word range. So it's the stress range, delta S or SA. Well, this might be a source of confusion. You see here we've indicated delta S or SE here. They are not the same thing as you see on the chart here. SE is A stands for the amplitude, SA is the stress amplitude, that one here, and delta S is the variation in stress, that's the range. So these two here are not the same. One is just a double of the other. And sometimes there might be confusion here, and we'll talk about that again later today. The important point here is that there is a change in your stress value. It doesn't remain constant. If it's a constant value, again, there could be breakage, but it will not be fatigue induced. So the cyclic range or the stress amplitude is really what matters here, and I think that's rather obvious to probably to most of us here. When the stress range, so when the variation of stress is big, it means that you submit your component to a big change, and the result will be that the life will be shorter. And I think it's kind of intuitive, and it's true. It's intuitive, and both intuitive and true. The higher the change in your stress, the lower the life in your component, because your item, your design is submitted to a big variation, and it's more difficult for the component to withstand such a high change in stress values. A second parameter that might affect the life and how long your component will be able to withstand a given repetition of cycles is so-called stress mean in the sense of average here. So the average of the stress here, we've got this sine wave here. The average value also plays a role in fatigue. So first and foremost, really, the main first indicator is the cyclic range. That's for sure. But also the mean stress is also important. It's a second parameter. It's not as important, but it bears some role also. So it's important also to characterize what is the value of the average of the stress. And specifically, depending on whether this average of stress is positive or negative, so whether or not we are dealing with tensile mean stress or compressive mean stress, that will result in that will be either beneficial or detrimental to a design. As highlighted here, when the stress is tensile, you tend to enlarge the small cracks. So for you, in the end, it will be detrimental, because you are really making it such that the small cracks that were that just started, they will extend, they will grow in size, and in the end, this will lead to a fatigue crack. On the other hand, when the stress and when the mean stress is negative, we are dealing with compressive mean stress, and that's good for our designer because on the other hand, here conversely, we're tending to reduce the cracks. So even though the crack might have started, having such a compressive mean stress means in the end we will compress it. We will compress the crack, so we will make it such that they will not grow, they will not extend. So that's beneficial to us. In turn, this leads to longer life. That's why not only the cyclic range is important when it comes to fatigue calculations, but also the value of the average of the mean stress. So these two parameters are really to be taken into consideration for any calculation that regards fatigue phenomena. So there, let's look at again, let's look in more details here at what really and how, what is the physics really behind the fatigue fracture. It's the initiation of the crack really starts when we at microscopic level in our structure, in our design, and there might be already some existing defects, and these defects, they will create some what is usually called slip bands. So you just imagine having, like, I think the analogy is very good here. It's just like shifting a deck of cards. So think here that we are having to do with a deck of cards here, and they will slip on one another here, and these slip bands they will form themselves along planes of maximum shear, and that's really what is responsible for surface extrusions and intrusions. We will create these defects here through these panes here, through these planes here, just sliding on top of each other. So that's how fatigue is starting, and then once we have sufficient energy, the crack might not, it depends, but it might become physically large compared to the microstructure of the material, and so that there is some energy change within your item, within your component. The flow of energy is modified due to these intrusions or extrusions in your design, and the result of this will be that there will be a concentration of stress at the crack tip, and having such a concentration of stress will make it such that the crack will in turn be able to propagate along the plane of maximum tensile stress. So that's the stress concentration at the crack tip here that will be responsible for the propagation of the fatigue defect. Stress concentration, it's the first time I'm using that word today. I'm going to reuse it and to explain in more detail why this is important when we have to deal with fatigue. So just to maybe, I think, to conclude this introduction on what fatigue is about and how it starts, first of all, there are two stages called stage 1 and stage 2. I'm not going to go into these details today. It's not about the theory of fatigue again, but just know that some cracks will be there. They are present within your material. We assume that there is pre-existing defect, but they will not grow large enough to propagate and to create a fatigue failure of your design. And indeed, we are lucky in this. Most of these cracks here, they will have insufficient energy to cross the grain barriers, so they will not propagate in the end. And that's good, of course. However, bear in mind that it only takes one big cycle to get the crack moving. So the boundary between the crack expanding and the fracture to propagate or not is really tiny here. A timeline of key events in fatigue analysis. Where do we stand here? Where does ENCODE comes into the picture here, and what are the big names in fatigue analysis? You might, for sure, even if you are new to fatigue, you might have heard of the name Voller It's after the German engineer August Wöhler in the 19th century, and that was one of the first one to practically really study fatigue. And this was after a train just derailed, and there was a train accident in Germany in those days here, and the emperor decided that they should know better why this happened, why this accident had happened, and Wöhler was in charge of studying the reasons for this fatigue to accident to happen. So you probably have heard that name Wöhler for the name Wöhler curves, and we're going to talk about those in the coming slide. Other names that might be known to you are Goodman or Smith-Watson-Topper. Goodman mean stress correction. I said earlier that the mean stress value was important, and Goodman mean stress correction is one way of accounting for the fact that the mean stress plays a role in your fatigue duration. So Goodman was the one to introduce a correction in the stress calculation so that the mean stress is taken into account. Then big names also are Miner, Palmgren Miner. They introduced the rule that we will use, and we will explain in more detail what is the Miner rule. Miner rule is basically the rule that's used for making fatigue calculation in our design. Okay. Yes, I hear some background noise. I don't know, but I hope you don't. Okay, other big names are Romberg Osgun, and that we will talk also when we talk about the different ways we have to calculate fatigue. And they account for a nonlinear relationship between stress and strain, and that could be useful when we have to deal with nonlinear calculation. And there is a Neuber-Thresh theory in the late 60s, well, in the early 60s, that takes account for the correction of stress when doing the calculation linearly, and we want to account for the non-linearities in the result in real life. And what do we stand here? ENCODE. ENCODE started really in the early 80s, so we've got like I think more than 40 years experience and knowledge in fatigue methods, algorithms. So I think we can we have some solid foundation, solid knowledge, and in fatigue calculation. So let's move now and let's give some examples of fatigue tragedies or fatigue incidents that happened in the past, and that were the reasons for people to study fatigue, just like Wöhler did in the 19th century. This happened in 1949, so you see it's not very old. It's just it's like 70 years ago. And there used to be a new kind of airplane. I think it was a British one, the G. Havilland Comet. It was a new program at that time, and it was the first jet airline to fly at higher altitudes as compared to previous planes here. It has a luxurious pressurized cabin, but however, it suffered from two tragic accidents due to fatigue failure. The end result was that 68 people were killed. That is dramatic. That's very bad. And the consequence of that is that 50 the orders really collapsed down, and the aircraft program, the Havilland Comet program, was suspended in the end. So the reason you see here, the reason we are mentioning this accident, this dramatic accident from the 1950s, is that the plane crashed due to fatigue failure. On the fuselage here, there were some fatigue lines created really in the fuselage, so it's a structural defect, and that led to fatigue. And one of the main reasons, there were a couple of reasons, but one of the main ones was that the window shape here was not rounded; it was rectangular, so it had some sharp corners, and that is perfect for gathering, for concentrating stress. And stress concentration factors are really something we as fatigue engineers disliked very much, because this is really detrimental to the fatigue behavior of our airplane. So to conclude this introduction to fatigue, again, if no equation you see here. The goal is not to bore you with math here, but really to give you the main ideas and principles that are responsible for fatigue. So to reiterate on that, what is fatigue? It's a progressive failure mode that's occurring under repetitive stress cycling. So there will be a number of cycles of varying stress, varying from high values to low values. And the number of cycles, this will be repeated over time. And this in turn could result into fatigue failures. It's been investigated for now more than 150 years. So there's quite a good knowledge base on fatigue, both empirical and theoretical. So we know quite much about fatigue today. So we have the means to fight against fatigue failures. We also mentioned that fatigue cracks, they start at the microscopic scale in our design. We assume that there are some flaws or imperfections, and these flaws might extend, might propagate, and might generate fatigue breakage. So that's what we say here, that the flow is already existing, and under some cyclic loading, some cyclic stresses that we repeat over time, this crack, starting from an existing, a pre-existing defect, might extend, might propagate, might grow, and might lead to failure. All right. And the last point here is that when we design properly our structure, we can resist fatigue failure. We can design in a way that accounts for all the dangers there is in not taking into account what fatigue could lead to. So we have the tools today. We have enough wealth, theoretical and both practical, empirical knowledge, so that we can design properly, having fatigue baked, so to speak, into our product. Okay, so that was for the introduction to fatigue. Now let's look at an overview of fatigue analysis and the various ways that we have available as today's engineers to fight against fatigue failures. How can we practically design, and how can we do things so that fatigue will not be an issue for us, or at least will be handled properly? So the roadmap is the following one. If you have already watched some HBK, some ENCODE's webinar, you're already familiar with this one. I think it's something very good in that in just one slide here, we synthesize, or we give an overview of what results, what creates fatigue. We call this the 5-box trick, the 5-trick box for fatigue. So 5 boxes here. What are those here, leading to fatigue results? In the center here, let me start with this one. So fatigue analysis here, what does it mean here? What does it mean here? It means we are simply going to analyze fatigue thanks to some algorithms. And these algorithms, they might vary depending if we're dealing with strain gauges that were measured on the field, or whether we're dealing with numerical calculation. But in any case, anyhow, there must be some way, some algorithm baked into one of the glyphs, one of our boxes for ENCODE to calculate things. So there must be some algorithm available for you to calculate fatigue with one of the ways we're going to detail in the coming minutes. The inputs stand on the left side here. These are the 3 main inputs you need to do a fatigue calculation. Which are they? First, on top here, there is the geometry. So there must be a way for you to characterize your geometry, the geometry of your design. Second comes the loading. What are the forces? What are the vibrations? What is the pressure my item is subjected to? That's the loading environment, and that one is also key too. These 3 inputs are key, of course. Geometry, loading, very, very important. That's why it's very important to characterize as much as possible the real loading conditions for your components. If you don't have the real loading environment, chances are you're designing in a way that's not robust. You might be off the picture because you are not calculating with the loads that your components will have to withstand once released in the field. And the final input, the third one here at the bottom, is the material properties. One component having a given geometry and being subjected to some kind of loadings will behave differently depending on what material it's made of. I think it's fairly obvious, but think of some item made out of plastic or made out of steel. Of course, given the same geometry and the same loading conditions, the behavior will be totally different. So material properties must be taken into account in doing fatigue calculation. Might be obvious to you, maybe not, but it's very important. So three main input: geometry, loading, material properties, and with that we can move further and calculate our fatigue results. Geometry will come in when we're dealing with practical measurements, will come in terms of stress concentrations and yes, typically stress concentrations values. Loading environments, that's what you must characterize in the field, or as much as possible, really you should strive for characterizing the ways your items are going to be used in real life by your end users. Otherwise, you are designing just in a way that's not appropriate. And I think that's very obvious. If you design for a given value of stress that is, say, I don't know, for the sake of the example, say 100 megapascal, and if you're in real life, indeed, your item will be subjected to twice this value, for sure the design is not robust because you have not anticipated those real values. So really, that's key, really. Strive for characterizing the loading conditions in the most accurate manner possible. Sometimes this is easy for me to say. So in real life, it's not easy to do because you have to collect data from the field and you have to make some measurements. So it's not an easy task, and it might even be a challenge in many cases. But it's really the only way through which you're going to design accurately, because then you will choose your design, you will change your diameters, the length, the radius of your designs in a way that will really withstand the real loading conditions. And again, I'm insisting here, this is really vital. The real loading conditions are key in designing in a way that's robust. Otherwise, you're just designing missing the big picture. And material properties, I talked about Voller. You probably heard this name before, Voller curve, and that is what we have here. We have a curve here. It might be a little small here, but we'll talk about that in more details. Don't worry. Here, that chart here simply translates how the material behaves in terms of fatigue. More about that in the coming minutes. In terms of fatigue roadmap and the various methodologies there are for addressing fatigue failures, as we said before already, there are three main routes. There is stress life, remember SN, S for stress. Then there is strain life with the EN method. E means deformation, so it's strain really. And there's the cry growth, which is the propagation of the growth once it's started. So three main strategies, three main ways to address fatigue, to calculate fatigue, are available. And depending on many things, and we're going to talk about these things in the coming slides, you might want to choose one or the other. And finally, what do we get to in the end? We have results in terms of hours. That's typical, but you could also express that in other units. It's just a repetition of the number of cycles that's permitted before you reach value. That's before you reach the failure. That's really what fatigue is. So it might make sense to express this number of repetition in terms of hours, but of course, it might be more meaningful for you, maybe if you're working in the car industry, to express that in the number of miles or kilometers that your car will be able to withstand before braking. Or if you are working in the aerospace industry, the number of flights, taking off, flying, landing, the number of flights, if that's a flight, the number of flights allowed for the fuselage before showing some stress, some fatigue weaknesses. So fatigue will be expressed in these terms: hours, miles, flights, repetition of the input loading. That's really how you will express fatigue results. And I think typically when designers in the car industry, when design the car or components of the car, it's really designed for withstanding a given number of kilometers, or it's typically 250 or 300,000 kilometers, or 15 years time. Well, this is how you would express warranty values, and fatigue is expressed in this same unit. So fatigue life, two stages. there is firstly the initiation of the crack, and then once this has started, the crack will or will not, depending on the loading, depending on many things, might expand, might propagate, reaching a total number of a given length on your item. That will be the total life. So crack initiation addition to crack growth is really what makes for the total life. Now, as regards the crack growth propagation, as we outline here on the last bullet point here, depending in the field you're working within, you might address or not crack growth. It depends on the strategy in your given line of business. Aeronautical engineers typically deal with fatigue in a way that's a bit different from the automotive industry engineers, for example, typically. So depending on your industry, you might want to consider crack growth or not, and you might want to have a different strategy for designing your items as regards fatigue. We're not going to deep dive into these strategies here, but this is just to give you the important point that depending on the field you're working within, the strategy you might want to use might differ. As for fatigue, there are three different areas, fatigue regimes, they're called fatigue regimes sometimes, and that really addresses what I was referring to before. Depending on your industry, you might want to design differently. Some parts, typically, we want to design them so that they will withstand a very long time, but it might not be necessarily the case. It might be the case that you design for a life that's not so long, so shorter life here for some reasons, and these reasons could be weight issues or cost also. You want to be cost effective, you want to reduce the cost. This will most probably result in having thicknesses that are thinner, or the materials chosen that are not as of high quality as they could be. In the end, your design will last a shorter amount of time, but if that's what you mean, if that's what you intend, and if that's under control, then it's fine. It's really up to you. You might finally tune your design so that you reach the amount of time or amount of kilometers that are demanded. So it's up to you. And typically we divide the fatigue lives in three areas. We have what we call the low cycle, to start with here on the left side here. That's a short, a limited number of cycles before fatigue happens. So not many cycles before there is fatigue. Then we reach the regime in the center part of the chart here, which is the high cycle fatigue regime here. So we need more cycles. Here you see we are reaching tens of thousands, even a million of cycles before there is fatigue rupture or fatigue breakage here. And finally here, there is the so-called infinite life. What does this mean here, infinite life? It simply means that fatigue will not be a problem for you. The stress amplitude or the stress values here are at value that is low enough for not creating fatigue in your component. And as a result, as an end result, if your component is not enduring fatigue, it will not break. It's just because the stress values are very low. So depending on the stress values, you might find yourself in one of these three areas here. Typically, when analyzing fatigue results, we have the low cycle, the high cycle, and the infinite life regime. And this is the first time we're seeing this sort of chart here. We're going to come back on this one here, but already it's interesting to notice what this represents. We have the stress amplitude here on the y-axis, and we have the number of cycles, the N that I was referring to before with the SN or the EN methodology. This N here, this capital N, stands for number of cycles. So we are seeing here, we are graphing the stress values versus the number of cycles. So how many cycles do we need for having failure at a given stress amplitude? So one of the points here on this line here means if we are sitting on the line here, it means we are failing here. So it's just a chart, a line that relates the stress value necessary to lead to fracture at a given number of repetitions of your loading, loading forces or stresses or pressures, well, whatever loading you have. So to reiterate on what we said, three main methods for calculating fatigue. We have the stress life. This is the historical approach. So if you have done already some fatigue calculation, chances are you've used the stress life and the Voller curve, because that's the very well-known historical approach towards fatigue. What do we say with stress life? We say that what really is the what drives the crack and what drives the fatigue failure is the stress value, hence the name stress life. So stress is really the main driver here. We want to see how stress will be imported in our item, because this will create, this could create fatigue. We say here that it works best for high cycle fatigue. If I come back on the previous slide here, this is the one in the middle here, the high cycle fatigue. So I need a high enough number of cycles before my component breaks. This is what we mean here. And stress life SN works really well in this area here, in this regime here. So whenever you have a high enough number of cycles before reaching failure, the SN methodology is appropriate. The second preferred way of calculating fatigue is the strain life. So EN this time. E stands for strain, so deformation. And physically, if we think of the physics behind fatigue, that's really what drives fatigue, the strain, right? Because when we have a material, an item that's subjective to loadings, it will deform itself and internally, and there will be a movement of the molecules within the item. And this is really this internal deformation that is responsible for the planes, the slippery planes we talked about. So really strain is the main driver, and physically that's really very, very accurate to say so. The big advantage of strain life over stress life is that it accounts for plasticity. It works at low cycle fatigue, and if we can come back on this one here, this is where really EN method, so strain life, works very well. On the contrary, SN will not work fine in this area, and the reason is just said here, it's outlined here. The reason is that strain life models plasticity, and that's a big differentiator with stress life, which does not. So that's one of the main fundamental differences between stress life and strain life. We'll come back on that later. So that are the two main methodology used for calculating fatigue: stress life, strain life. And there's then crack growth, which is a bit different, very much used in the aerospace industry typically. It is driven by this so-called stress intensity factor. So it's a bit different than stress or strain for being the main inputs into fatigue. But it's very useful when you have to evaluate how the crack will propagate and will extend over time. Here we are assuming the existence of a crack or a flaw in the design. So that's a particular topic here. Today we're not going to really talk much about crack growth. We have things though in our software that address this topic of crack growth. So if you believe, or if in your industry crack growth is important, be assured that within our ENCODE software there are tools that can help you. But today we're not going to focus on crack growth. All right, so let's look at some important factors for calculating fatigue, and let's make this analogy that will speak, I'm sure, to everyone, which is the bank account analogy. What is important when dealing with fatigue? We said there is the cycle size, and for sure that's one key driver for fatigue. How much does the stress or strain, depending on whether we're using SN or EN methodology, so stress or strains, it depends. So the point is, how much do they change? What are the variations of strain in my design? How much? So that's in terms of cycle size here. We see here we have a big cycle followed by a small cycle. followed by a second small cycle. There could be a fourth bigger or small cycle, it depends. So how much does this change over time? But again, the peak stress is not enough information, and fatigue, as stated already, only happens when you repeat things, when you have varying stresses. So this variation of stress here needs to be repeated. And that's so that's number one, the cycle size, and number two is the cycle counting. So how many of these cycles are there somehow hidden within our load time history of pressure, of force, of stress. So how many cycles do I have, do I subject my component to in real life? And then when talking about these cycles here, are they all the same size? They could be repeating cycles of all having all the same size, and that would lead to fatigue. That could lead to fatigue failure. That could be fine as long as we have cycles. That's okay. We have fatigue. Now in real life, things might be a little bit more complicated. Real life signals are often not stationary. They vary. They are often complicated in one word. So do they vary, these cycles? It could be really the case. In real life, you might have a big cycle followed by small cycles, then a lot of small cycles, and then the loading increases again. So the cycles, not only do they have to be there, but they might vary in size. So each cycle might vary in size. More on that to come. So the bank analogy I was referring to is, I think, is good for understanding fatigue. Fatigue is just like the bank account you have on your the money you've got on your bank account. So you could withdraw everything in one go, but that will not be fatigue. Or you could go to the ATM machine and make cash withdrawals every now and then, and that will be very much in par with fatigue. How often and how much each time I go to the ATM machine, how often and how much money every time I go for withdrawing cash, how much money do I take from my bank account? You could go and withdraw 100 euros tomorrow, 10 euros, and then the day after 20 euros, and so on, and you will repeat that. And at the end of the month, might be that you've exceeded what was provided to you by your employer at the beginning of the month, and you're broke, no money anymore. And that's very much the analogy there is with fatigue. Fatigue will take out of your design some capacity to withstand the failure. It's just like when you're withdrawing money on your bank account. At some point, there is no money left. It's the same for fatigue. At some point, after withdrawing some capacity from your design, there will be no possibility for your design to withstand you spending money. So there will be no capacity for the design to withstand the loading, and it will fail. It will be broke somehow. So I think this bank account analogy is very fine. It expresses the idea that stands behind fatigue pretty well. So I hope I'm not going too fast. We are reaching now the overview of fatigue analysis. So what do we need for doing fatigue calculations? We have seen before, remember this 5-box chart here that we covered some minutes ago. We had 3 different inputs for fatigue. Loading, well, we started on top, geometry, then there was loading, and then there was the material aspect there is in fatigue. So these 3, you cannot do any fatigue calculation if you don't have all of these 3 characterized well enough. And again, I'm insisting on the loading part. Loading part tends to be something that people just overlook, just assuming some random loading or some loading that comes from standards, from regulations. That might be good if you don't have any data at hand to do things. So in the first phases or in the first iterations of your design, that might be good. But as soon as your design matures and before when it's about to reach production, make sure you've designed and you've validated your design with loading that really represents the real loading conditions your end users might import on your design. That's often called mission profile, if you've heard that name before. That's key, and I'm insisting on that here because it's often overlooked by newcomers in the world of fatigue calculation. They just assume some generic loading. They do the design the best they can, and that's fine. But having missed the right loading in the first place will result in their design not being robust against real life conditions. So I'm maybe a bit repetitive here, but it's really vital to take into account the right loading when designing your items, your components. So that were for the inputs to fatigue calculation. As for the computational methods, there are mainly three of them. Crack growth, as we said, and the two we are going to focus today on: stress life and strain life. So that concludes our extended, I should say, introduction to fatigue. I hope now you've got some firm and clear ideas about the concepts that we're going to develop in the remaining of this seminar. And finally, yeah, I forgot, but this one, the fatigue includes, there's both the crack and crack initiation, and then the crack propagates or not, depending on the various loadings, depending on the design, depending on many things. But total life, there is crack initiation and crack propagation until the fracture. That's total fatigue. And the last point is that fatigue life is a statistical answer. We are going to see that when we will look at the ways and the curves, the SN curve or the EN curve, the Voller curve somehow, how these curves are characterized, it will be very clear that fatigue is a statistical answer. So there is some variation, and we need to fit the laws in the way we characterize things. But never forget that fatigue is a statistical result, and as such, there are some things to consider when giving a result in terms of fatigue, and more on that also in the remainder of this presentation. Okay, let's now start by looking at the stress life method, the SN method. Again, if you forgot, what is this N here, this capital N? It means the number of cycles. So stress life here is just the same as this N here. N is the number of cycles, so it's the it is expressed in terms of repetitions. So it's the life in it. That's why we call it stress life also sometimes. Remember when I said fatigue results are expressed in terms of hours or kilometers or number of flights. That's the life we're talking about. And this life is expressed really well by the number of cycles there is within our signals, within our loadings. So let's start today by looking at this first route you have. Remember, you have three of them, three choices. Let's look at this first one, the stress life method. First, let me remind you of this, the so-called similitude principle. You might have learned this before in college or earlier. What does this mean here, really? Well, this is a concept that expresses that the number of cycles to failure in the component, so here on the right side we have a component, a real-life component, is just the same as the one that would be necessary for failure for the test specimen, this test coupon here, as long as both experience similar stresses. So when both experience similar stresses, so hence the name simulated here, simulated principle, the number of cycles to failures will be the same in both cases. So there is this simulated principle in the stress life method, and that's one of the key motivation for the stress life methodology. Okay, so let's look now. We are looking specifically at the stress life method. So this chart here that was generic. Let's now be specific in terms of the SN method, stress life method. What are the inputs really needed for calculating fatigue? The first box here on top, geometry, will be either a stress concentration, or sometimes it's expressed in terms of a KF. It's a concentration fact. It's just a factor. It's a parameter that allows to express the stress concentration in our design. So that is for the geometry part. Then, in terms of loading, we will look at the amplitude stress histories. So remember, we're dealing with the stress life method right now. So we're going to look at the stress history. Now, this stress history could be constant or variable amplitude. When we say constant or variable amplitude, it's just the amplitude that remains constant. Don't be confused here. Sometimes people get confused. Constant amplitude doesn't mean the signal is constant. It just means the amplitudes are constant. We might go from high to low, same numbers, and that's the constant amplitude. But the signal contains some cycles. So we are never dealing with a constant flat signal. That's just I'm drawing your attention on that here. We need some stress variation, and the stress history is just that. It's looking at the stress variation there is in the loading. The third parameter, the third input, is the stress life curve, sometimes called Voller curve. There are different formulations. What does it mean here? It means we need a way to express the number of cycles, to relate the amplitude of the stress with the number of cycles that my component can withstand at that given stress value. And the stress life curve is just that. It's a curve, it's a line that expresses the relationship that exists between the stress and the number of cycles that the component can withstand at that given stress. And then the algorithm we're going to use here for the stress life method will be to calculate the cycles. We said the cycles are very important. So from our stress history, we need to find cycles. We need a way to break down our signals into cycles. We're going to talk about that in the coming minutes. That's the cycle counting methodology. And then once we have the damage for each cycle, we'll be able to apply Manners rules. So this way of calculating fatigue here, that's expressed in this box here, we just express the cycle count, the damage per cycle, and Manners rules. If you're new to fatigue, don't worry, we're going to cover this in great detail in the coming minutes. And finally, you will be able to calculate your fatigue results in this using a given algorithm that's using these three inputs here. So let's focus on the stress life curve. So this one here, the one you see on the right side here, is the SN curve. So what do we have here? Well, the name is after August Voller, as I said. So remember in the 19th century, so a while back now, August Voller, what did he do to study why the train had an accident? Well, he devised a tool for evaluating the number of cycles that the train axle could withstand at a given load. And that's really the result of the Voller curve here. We're going, the different circles you see here are the different component specimens that we're going to test. So we have, here we have 1, 2, 3, 4, 5, 6, 7, 8 points here, which means we've tested 7 specimens here. And for each of them, we decided we fixed the load, say. Here we have roughly 700 Newton, for example, here. Well, what does this mean here at this point? It means that at this given value of 700 Newton here, that component is able to withstand a 10 to the power, yes, it's 10,000, or yeah, roughly a bit more than maybe 20,000 cycles here. And the process for obtaining such a curve is to repeat that for many components. So we would obtain different points depending on the varying load here. So we know for each loading condition what is the number of cycles permissible, acceptable in my design. Or you could look at it the other way around. You could say, okay, I know that I want to design for this given number of cycles. What is the allowable maximum load range in my design? So two ways to look at the Voller curve. The main, or one of the drawback or disadvantage of the Voller curve is that you need a component fatigue curve to predict the component life. What do we mean by component fatigue curve here? We mean we just look at the component as already engineered here. So this curve here, really refers to that component already existing in the field here in the wild. So that's somehow a drawback. And to address that point here, we've come with methodologies that are more standardized and that allow you to characterize in a lab your material. And that's what we're going to talk about now. How do we characterize in a lab our material so that we can make calculations that are very generic and very broadly applicable? So the principle is just the same. We just want to test different coupons. So that in the end we will have many points, each referring to a given loading condition. So here, all these red dots here you see on the chart here, they represent a component, a test coupon, test coupon that's been tested in the lab here, given some at a given load here. We have a machine that's designed for that. It will create some tension and stress compression into our test coupon, and after you repeat this compression, tension, compression, tension, you repeat that over time. Remember, what we want is to vary the stress, otherwise there is no fatigue. So you repeat this process of compressing, extending, the test coupon, and at the given number of repetition of this cyclic loading here, there will be a point in time, so in number of cycles, where your component will break. And you report that on the chart here for your coupon. And you repeat that for the various different loading values here. And you've got these points here, similar to the ones we see on the chart here. This is an example of a typical chart we obtain when doing such measurements in our lab here. You could see different things. You can see, first of all, that you have many points here, and we're going to express and to tell in the coming slides how do we deal with these points here, because you see here, for example, for this 50 psi here, we've got 3 points here. So which one shall we take? Shall we take the first one, the last one, the one in the middle? We have to make some assumptions for taking that into account. And another point here is that fatigue characterization could take a long time, depending on how quickly you are submitting the loading, the tension, and extension on your test coupon. Depending on the frequency of this loading, your test might vary from 1 day, okay, if you cycle at 10 hertz, but it could be at a lower loading, it could be that the component will not break until they've been submitted to 1 year cycling in testing. So it could be very time consuming to have this material characterization. So testing fatigue test and characterization is costly because, of course, you need the equipment, you need the right knowledge, but also because it takes time. So you need to have the equipment available in your lab for a long amount of time. So that's the drawback. You need to, but you need those, right? You can't do without any fatigue SN curve. So you need to have those available. Otherwise, you can't make any fatigue calculation. In our software, with ENCODE software, we have material database that comes with many materials that we have tested in our lab. So, if you're using our software, you've got access to a database with many materials characterized in terms of fatigue by people who are really experts in that, so that you can safely use their testing results in your calculation. The concept of endurance limit is the one we already touched upon in passing before with the infinite life regime. If you remember, there is a point in stress value, and some materials exhibit some do, some do not. Some materials might exhibit what we call the endurance limit, and this is the value below which there will be no failure, no fracture. Sometimes you might want to design based on this value, this endurance limit, and it's fairly understandable. You say, okay, I'm going to make my design such that the loading will be the energy in my component will be allocated in ways that it will not exceed a given value, so that I'm designing safely here, because these values are so low that my component doesn't get fatigue phenomena due to these loadings here. However, the endurance limit does not always exist for all materials, so this concept is not always applicable. So To define the endurance, the SN curve, sorry, the SN curve, the Voller curve, but it should rather be called SN curve. Again, this relates to stress values, to the number of cycles. We have to make some kind of assumption. This is what we referred before when we said that fatigue is a statistical phenomenon. And why is it such? Well, you see here that at a given value of stress range here, we have three dots here, three crosses here. And what does this mean here? It means that we have to make a choice. So what do we do? And here, what we say here is that we make a fitting of that curve. Typically, it's a least square regression, but there is some kind of assumption you make here to get to the distribution of the stress versus the number of cycles that lead to failure. Before you are able to reach, to get to this straight line here, you need to make such an assumption when doing the fitting. And that's what you do after having collected the data points in the lab. Once you've done this fitting curve here, the red line we see here, you reach the, you're able to express that in terms of a straight line equation, and that's the so-called, that's the SN equation. So it relates again the stress range for each cycle, there is a stress range, to the number of, this one here, the number of failures before reaching fracture, before failing your component. And these two, the stress range and the number of failures, are related through two coefficients here, through two parameters, this sigma f prime here and this little exponent here, this b parameter here. That's really this one here, it's also sometimes called the stress range intercept. This is where the straight line here intercepts with the y-axis here. And this one here, the little b here, is the slope of the curve here. So, and this one is extremely important, this coefficient b here, because it is the slope. Just imagine having different slopes means having totally different results in terms of material behavior. So this little b here is key in fatigue predictions calculations. So to reiterate the important SN curve parameters, which are they? The first one is the range of the stress cycle, so delta sigma here. And the second one, that's for defining the SN curve. The second one is the number of cycles that lead to failure. And the two important parameters are this stress range intercept here, where the line intercepts the y-axis, and this little b here, which is the slope of the SN curve. And these are, as stated here, these are really material properties. They depend only on your material. So they can be characterized on test coupon in a lab, and you can reuse this this database, this stress life behaviors in your calculation. Typical values for the B slopes are the ones shown here. One, if you're dealing with electronical components, it's minus 0.25. And for welded components, it's very particular for welding components. We have a lot of webinars dedicated to welding. So welding is kind of complex to calculate in terms of fatigue, but we have things dedicated for welding. And here, we just say roughly, we just say in a nutshell here that when you have welding issues, the welding is really what matters. No matter really what kind of materials you're using, welding is really what matters. How good is your welding? And for welding components, typically we will use this value here, minus 0.33 for the slope of the SN curve. Okay. A little, yes, a couple of words again on the fact that fatigue is a statistical result. Earlier, I just said that fatigue needs some fitting. We want to reach a distribution curve. We want to make some fitting on the points that have been measured in the lab here. And this is where probability and statistics come into the game here. What we do typically is that we will make the fit, the regression, saying so that we have a 50% survival. So if we look at the distribution of the points, remember for one stress range, we might have different points for breaking here, for at least to failure. What we're simply saying here typically is we say we have one chance into a failure when we are using the red line here. That's typically what we do also in the software. So that's fair enough. But chances are you will want to design with a higher confidence, not confidence, but how can I say this? You want to have a higher certainty of when your item will fail or not. And typically that's the 95% percent survival confidence level you want to achieve. So how do you do that? Well, simply enough, you just shift the S&P curve downwards. Doing so allows you to be more conservative, as is obvious, because for a given stress range, the number of cycles to failure will be lower. So you might just want to shift down the SN curve in your calculation, so you account for more certainty. You are sure that you will have 95% survival. So that's why we said that fatigue is a statistical phenomenon, and there's probability in it. Whenever we express a result in terms of fatigue, we should have this in mind. We should not forget this. There is probability involved in fatigue. There are some advanced studies, sometimes are called probabilistic fatigue calculations, and we can do some of the things at ENCODE. It's an advanced topic, but just know for today, just remember this out of the seminar this morning: fatigue is a probabilistic phenomenon, and there are some assumptions made in your fatigue calculations. Not meaning it's not useful. You just have to have this in mind. Okay, stress concentrations and notches. Remember when I talked about the Haviland program, the English program in the 50s, that where the airplanes just crashed, and that was the end of the program. I mentioned the word stress concentrations, and that was one of the reasons for the fuselage to break down. So stress concentration and notches are responsible for many or most of the fatigue failures. We have to address them appropriately. So let's look at this now. I'm just hesitating. Maybe it's time for the break. Yes. Before we embark on this, I think we all will appreciate the coffee break. So let's just stop for now for 10 minutes, and then we'll continue the seminar. So on my clock, it's 32 past. So let's start again in 10 minutes. So 42 past the hour. So see you in 10 minutes.
Nicolas, can you please unmute yourself?
Unmute me. Okay. Now I should be unmuted. Do you hear me now?
Thank you. We can
Okay.
hear you now.
Okay.
Fantastic. Thank
Okay.
you.
Okay. So let's move. Let's focus on the stress concentration and notches for the second half of this of today's seminar. Strain gauges, you might be very familiar with those, and they are very useful practically when we want to measure the strains on our component. What we will calculate, measure, sorry, is rather measure rather than calculate. Sorry, we measure the nominal stresses using the strain gauges, and typically there are places where the strain gauges they cannot be placed because of some holes and some areas, some radii that impede us from placing the gauges there. So we what and however, this is very important to be able to predict the stress in areas such as, for example, this one here, typically in the corner here, because the stress concentrations might be higher there. So what we want to do is we need a way to get from to get the hotspot, we call the hotspot, the high value stresses, from stresses or strains that are measured at places where the stress and the strain values are nominal. So that's very important to be able to somehow translate nominal values into high value hotspot stresses or strains. Both are possible. Stress concentration factors, probably you are familiar with these ones. Typically, when we have sharp radii for windows and for panels, when we have some, here we have a very good example, I think that's real life. And I've been struck by this in my previous job. Really, I was designing a bracket in the car industry, and I've seen this really happening on the bracket that's used to make a connection between the tank of the car to the car chassis. And we have really these embossings here, or these serial numbers here. They will create some high stress concentrations. And indeed, in my previous job, we had the logo of the car maker that was there, and the bracket was just cut there, just at the logo of the car maker. So stress concentrations, seriously, are very important. And typically, when you have serial numbers, printings like this, or sharp radius, that's very bad in terms of design. So you should pay a lot of attention if you have such designs. How do we do this? I said we had to find a way from reaching the nominal measured strain values to the one where the strain is higher, so the hotspot areas. And for that, we will simply modify the SN curve. So the green curve you see here is the one that's unnudged, meaning we don't take into account stress concentrations, holes, embossings, imprintings, serial numbers, imprints, all our designs. We just believe our item, our material is perfect somehow, with no real life trouble, if I can say this generically. But the thing is that in real life, we have these things, as we've seen before. We have these holes here. We have this sharp radii here. We have to take those into account, really, if we want our design to be accurate. And for that, in terms of fatigue, we will modify the SN curve, and we will modify it with this KF concentration factor. It's a value here that you are using to shifting downwards your SN curve, so that it takes into account the fact that in real life you will have stress concentration factors. So the notches, the particularities you have in your design, they are very well addressed by modifying the SN curve in that manner here. In this example here, we gave it was an airplane, the A380 failure here, and the reason for the failure was that there was oil, high pressure oil, that leaked throughout the where it should not have leaked. So the oil leaked, and there was a small crack first of all, and then the oil leaked, and the leaking of that oil was dramatic, and ultimately there was fire on the engine. So that's reported. It was 10 years ago or so, and you see the end result of this of the engine here. So the reason was that there was a a crack, a fatigue failure crack in a stop pipe, and this little crack allowed the oil to leak through. So you see, when we say fatigue failures are responsible for so many incidents in real life, not only fatigue failures per se, but also for the consequences they result in. And in that case, it was oil leaking through the crack. Okay, let's get back on Maynard's rules and the variable cycles idea I referred to before. I mentioned the word minor. If you remember Penguin's minor, that's one of the key rules we use in fatigue calculation. It's very simple. No worries if you have never heard that rule before. It's a very simple concept to understand. Fatigue loading. We're back here. Fatigue loading is one of the key inputs. If you remember, there are three of them: geometry, curve, material properties, and fatigue loading. So the fatigue loading could be in different shapes. They could be a constant amplitude loading. If we're looking at the stress variation here, this will generate fatigue because the stress is varying. So we have cycles here. We have a given number of cycles here. In the first case here, in that one, we said that it's constant amplitude because the maximum values and the minimum values remain the same. So we label this one constant amplitude loading. In real life, chances are you might have, well, in a testing environment, you might rather want to have constant amplitude, but in blocks. So this is what we have in the second chart here. So we have a first block here. At this, it's a constant amplitude loading, but then there's a new sort of blocks here. It's again constant amplitude loading. Simply, the different thing here is that we have reduced the stress values, and then finally here, the third kind of block here, we have increased the stress values. But we have a sequence of 3 blocks here, so we call this block loading. It's block constant amplitude loading rather. And finally, a typical loading that you might measure from real life measurements on the field would be what we call variable amplitude here. So you see here, there is no simple one value here and the second value here. Now, here you have really a sequence of max and mins that vary over time, and it's not easy to see the cycles as it was on this constant amplitude or even on the block loading. Here, it's more something really that's, we have trouble in finding the cycles here. So there are ways to address such loadings that result from real life measurements, and more on that in a minute. Maynard's rules. Let's get back on this bank account analogy we had before. And Maynard's rules is just this in the end. Think of fatigue failure just as you withdrawing money on the cash withdrawal machine. So you will have some number of cycles repeated over time, and your component is able to withstand a given number of these cycles at a given amplitude. So each time you will withdraw money, it's the same as in engineering, from an engineering perspective, as importing a loading force on your component for a given number of cycles. So each of these cycles, let me get back here. These cycles here, the one we see here, they will fatigue your component. They will induce some fatigue mechanism within your component here. So here we've applied them for a given number of cycles, and maybe it is that what we will do here, we will calculate the amount of fatigue these small n1 cycles here have generated within our component. And how do we do this? Well, we say that we are looking at the SN curve, and we know that this component can withstand n, this capital N number of cycles before failure here. So we simply calculate the ratio of the number of cycles that have been impacted at a given time on our component, and we calculate the ratio with the amount of cycles that the component is able to withstand before failing. And so this relative number here gives us a relative fatigue number due to this first cycling N1 cycles here at this given S1 amplitude. And we will repeat that for the second block here. We just do the same calculation. This time in turn, we have N2 cycles. So we will calculate So that's why you have a sum here over the different blocks here. So for the n2 cycles at another stress amplitude, we will have another fatigue value in our component. And finally, we just sum them all these block cycles, and that's the total, that's the final fatigue calculation. And Mayer rules simply says this. It says two things. It says first, we can sum this, we can accumulate, fatigue accumulates, you can sum these fatigue things. That's number one, what Mayer's rule says. You can just sum them simply enough. So theoretically, it's more complicated than that. Sure, some of you might wonder, is it really true? Can I just sum this? What is the effect of having big cycles before small cycles, or does this have an influence? The answer is yes, it has. But in reality, we see that Mayer's rules in real life, we see applies very well. So even though theory might be even more complicated, practically, we know from years of practice that Mayer's rules apply very well. So don't bother yourself having this complicated, well, you could if you're doing research and things like that, but if you're practical, if you're an engineer working on your design, you can safely assume Mayer's rules work fine, and this will be the case in most of your cases. So Mayer rule says two things. First of all, we can accumulate the damage, and Mayer, so it's like the amount of life in your budget that's been consumed. And Mayer rule second says that once this value that you have calculated during the summation reaches 1, we say we have no budget anymore. So there is no life anymore in your item. So there is failure. It breaks. So that's Mayer rules. Two things. Fatigue can be accumulates over time. And when the fatigue calculation numbers, when summed in that way, reach 1, the value of 1, then it means there is breaking, there is fatigue failure. So you see, Mayer's rules is very, very, very simple. That's what I was explaining to you before here. Each of these blocks here will bear some fatigue, and then we simply sum them all. So again, just to re-explain again, these ny cycles here, they will induce some fatigue because of this delta sigma 1 here. So the fatigue they will induce, it will be the number of cycles during which they are applied, this n1 here, times 1 over the number of cycles that my component can withstand given this stress range value here. So I'm referring this one here. What does it come from? It's referring to Wöhler's curve, the SN life, the SN curve, the stress life curve allows me to retrieve this value that tells me how many cycles my component can withstand at a given load. And when in real life, when I've got such a cycle view of my signal here, I can simply multiply this number of cycles by the inverse of the number allowed. And that's my relative damage for that block here. And then minus is here. Minus says we can make the summation. And finally, we reach our total life, which is just the inverse of the total damage here. So the total life will be 1 over the summation of the relative damage calculated through from each block cycle here. Okay. So this is just an illustration with a practical case here. And again, what Mayer says is that when this number calculated during the summations of the various blocks here, when this number reaches the value of 1 or above, we say we have failure due to fatigue. And the life, what is the value of life? So there are two results in terms of fatigue. When you will express your results in terms of fatigue, there will be you have two ways mainly to express your result. First, you could give a number, the damage value, the so-called damage value. It could be a number, it could be a very small number, it could be 0.001, for example. That's the damage value. And the second way of expressing your results will be in terms of life. And the life, which is 1 over the damage value, is the number of repetition of your input cycle. So very often newcomers to the field of fatigue are puzzled by the meaning of life here. What does it mean really when I express my result in terms of life? Well, it simply says that say you have 2, say that your life is 2. It means here, in this particular case here, it means that you could repeat this sequence here, assume it lasts for 1 hour. If your final result is life equals to 2, it means that you will reach failure when you repeat this loading during 2 hours, 2 times 1 hour. So that's just the way to look at the life and to interpret the life result. It's the number of repetition of the input signal, the input sequence you have as loading conditions. Okay, the same example here with the figures instead here. We are, I think it makes it very easy for you to understand how all this works. We have, let's look at this one here. We have this stress range here of 100 here. So we'll pick the number of value here at a given stress range of 100 here. And this gives us the number of repetitions that are permitted before reaching failure. Since we have replicated that one here only 6 times, the relative failure imparted into the component due to that first block here, this first one here, will be 6 divided by this big number here, the number of failures. And we repeat that for each and every block cycle. For 80, we look at the stress life curve, the Voller curve, that's the red line here. We'll pick up the number, the range value here for this second block here, which was 80 megapascal here. 80 megapascal allows me to repeat, well, there will be fracture when I've got 1 million repetition of these cycles here, because of this number here. I've repeated that 12 times, so the relative amount of failure I will induce in my component is 12 over 1 million. And that's for the second block. And I just do that for each and every block I have been able to identify in my loading sequence here. And finally, I reach that number here, which is the total damage I was referring to before. In this case, it's a small number, and here it's less than 1, so it's good. We still have some budget to be consumed before breaking. And we can also express, as I was saying, in terms of life, doing the inverse of this. This will give us the number of times I can repeat that signal here before failing my component. This technique, this Miner's rule, we can use it both for the SN and the one we've talked mainly so far, and EN is to come. SN and EN, so stress life and strain life fatigue techniques, can both use Miner's rule and this accumulation rule to calculate the damage value. They are valid for both routes, both strategies. To conclude on the stress life method, what is it about? What is the stress life method is also sometimes called SN. So again, N is the number of cycles. That's what the capital N stands for here. So the stress life method, what does it do? It relates stress cycles, remember the range of the stress values, to the fatigue life, the number of cycles you can have before reaching failure, through an SN curve. So the stress life method really is just about that. We have a given value of range, we have a given range of stress, and we want to relate that to the number of cycles that will lead to failure. We need such a curve before doing any fatigue calculation. Otherwise, there is one of the 3 inputs we are talking about missing, and we can't do anything. So we need a material SN curve. And the material SN curve, it's the relationship between stress and number of cycles for a given material. And as we outlined briefly, we need to make some corrections. Typically, when you have notches, remember when we shifted the curve downwards, or when you have starting the presentation, the seminar today, I mentioned the mean value of the stress that has an effect also, if you remember. This must be taken into account. So we might need to to amend the stress curve so that it really reflects both our real life components, and also it takes into account really fully the loading conditions. However, the stress life method suffers from some limitation. And the most notorious one being that it does not apply for low cycle fatigue. Low cycle fatigue, if you are in that situation, choosing a stress life approach is not valid because really stress life is not fit for that. For that, we will use the other approach in a minute, which is the EN approach. So a serious limitation for when using stress life method is whether or not where do you stand in the three fatigue regimes we've seen. Is it low cycle, high cycle, or infinite life? If you're in the low cycle, which means a small number of repetitions before failure, typically it's fairly obvious. If you have a small number of repetition, it means the loading is high, and typically you will have plasticity, and stress life doesn't account for that. So low cycle fatigue, stress life is not fit for it. We also mentioned in passing that some materials have a so-called endurance limit, but depending on the kind of loading you have, this endurance limit can vanish somehow. And even more than this, some materials do not at all have this endurance limit existing per se. So endurance limit is an idea, is something to be taken with care. And one of the warnings, or the warning alert I was hinting at when starting today's seminar, is that it's very easy to make a mistake when dealing with fatigue calculation and the stress life curve. The stress life curve, does it relate the stress range or the stress amplitude? If you remember the sine wave we had in the first minutes of this presentation, we had a sine wave, and there was the stress range, delta sigma, and there was the stress amplitude. These are two different things, one being the double of the other, and mixing the two, of course, will have traumatic consequences for your results. So, and the thing is that whether we're considering SN, what we've seen so far, or EN, we don't use the same value. In one case, we use the range, that's for the stress life, and in the other case, for the EN methodology, we will use the stress amplitude. So in case you would be doing calculation by hand with Excel, or with some spreadsheet tool, and doing things by hand, be very, very, very cautious not to mix stress amplitude or stress range when doing the calculations. Otherwise, your fatigue results might be totally wrong. With ENCODE, you don't have to worry. Everything will be done transparently for you. There is no way to make that mistake. So that's the benefit of using a software that's dedicated to such calculation. And finally, just to reiterate also that fatigue is a statistical phenomenon. We have some probability calculation, probability fits for deriving the curves. So these are constant that we get from experiment, from measurements. So never forget that fatigue is never an absolute value that you give like this. It's always, it bears in, it's baked, well, statistics and probabilities are really baked within your stress result calculations. Strengths, weaknesses, and applications of the SN, the stress life methodology. Strengths, so the strong points of these methods, let's start with those here. It's simple, yes, that's true, and it's been used for decades now, really more than 100 years. So it's very well known also, so there is a lot of existing SN data and experience, very used by most practitioners in the field of fatigue. It's good for the case of long lives, so when you are in a high cycle regime, that's fine. It's good for constant amplitude loading, so a lot of trends and that explain why you would want to use the SN, or to choose the SN approach for making your life calculation. However, it suffers from some weaknesses. Amongst those are the fact that it's difficult to extrapolate, that's one thing, but I think more predominantly the SN methodology, and let me focus on this one here, totally ignores plasticity. Plasticity, by definition, is not included, is not baked into the SN methodology. So as soon as you are having some plasticity phenomena occurring in your component, in your design, then the right choice is not the SN methodology. Not to say it shall not be used. You just have to know whether or not it's fine to use it, and you have to know the weakness of the SN methodology. And hopefully this seminar helps in highlighting this caution or mistakes or traps one might fall if ignoring that aspect. The application of the SN methodology are very wide, and it provides a very quick estimate of life. It's very easy to put in practice. Even you could do it with a spreadsheet if you have the will to do so. It's not so easy, but it could be possible in a spreadsheet for simple loadings. As soon as your loading becomes realistic with things that you've measured in the field, doing that on a spreadsheet, I think becomes very difficult, if not impossible. Okay, I have talked a lot. Maybe it's time to switch and to show you how we can do that practically with our software, with our ENCODE software. So I'm going to switch on the software side now here, so that you see how easy it is to do these calculations within ENCODE GlyphWorks. So let me move here, and now you should, if everything goes well, you should see my my GlyphWorks interface here.
Yes, we do see it. Thank you, Nicolas.
Great, wonderful. Okay, so that's the interface. Some of you might be totally new to ENCODE, so just in a couple of words, what is it about and what is the interface? How is the interface built? You see on the left side here, you've got the ENCODE software packages. You see we have GlyphWorks, Design Life. That's the two we're going to use today. There is Vibesys and others. On the right side, here I could just do that. We have all the what we call glyphs. The name of the software is GlyphWorks, and these boxes here, we call them glyph in the software terminology. What are those glyphs? These are boxes that contain a lot of software or of engineering knowledge here. These are little functions that encapsulate really knowledge, design, engineering, mathematical knowledge, algorithms are just embedded into those here. For example, here, see if you want to calculate a frequency spectrum, or if you're to deal with electric power. It's very common nowadays. There's a high need on the market to study electrical vehicles. So we have come up with a glyphs that's really dedicated to that. You can calculate many things that regards electric power. Well, you see here, there are many things you can do with these glyphs. Just drag and drop them here. Yes, I just said the word drag and drop. Everything is graphical in our software. So you don't have to write any code. You don't have to write any difficult code that only a couple of people can understand. It's very simple because it's graphical. So here I've already pre-built this flow for you. We call this a flow. This way of connecting the glyphs here, we call this a flow of analysis. I've done it for you here before in the interest of time, but what you do in the software, here you see I'm just dragging and drop things here. So I'm dragging and drop things, and then I will connect the boxes just graphically here. I could just do that and connect this one to that one and have some display here already. You see, just very simply to drag and drop things. If you have never used our software before, it's really easy to get started with. Just drag and drop things on the main interface. The main interface being this workspace here, that is intended to collect the glyphs you have on your right side here on the glyph palette. And using these blocks here, these fundamental blocks of knowledge, of engineering knowledge, you will be able to calculate things, do a lot of things in signal processing. Here, this flow, as I said, it's called a flow. It's intended to calculate the results of your fatigue strain gauges measurements. So here, what do we have? On the left side, there's the tree view of the available data, the things you've gathered, you as a test engineer or your test engineers colleagues. They've been on the ground, on the field, they made some recordings. And finally, your task is to calculate the fatigue out of these strain gauges results here. So we see here, we've got 5 channels here. GlyphWorks works for many channels at the same time. So I don't need to repeat this process 5 times. And I just have one file that will drag and drop on the input glyph here, and the result will be calculated for each and every channel. I never have to do things to repeat things for doing such things. GlyphWorks does automatically this for me. I've just got 5 here, but say I had 100, same story. GlyphWorks does this automatically for us. So how I do this? How do I do this? Well, let me just drag and drop here. Here it is. So this is my seminar here. I could. This is a very interactive view of the inputs here. And usually that's the first thing you want to do, right? When you have some data coming from the field, you want to see what it looks like. With Glyphworks, it's just as simple as dragging the file on the main interface here, and you have this display available right away. It's interactive, you can do many things. I'm zooming here. You can add some cursors. Here, X cursor here. You see you could move them. Well, you get it. I'm not going to do a software training here, but this is just for showing people who are new to our software how easy it is to visualize things graphically with our doing things graphically. Here I can right click, create all cursor, yes, and I'm fine here. So here I'm going to choose 5 channels, and here they are. Okay, so let me remove that. Let's do it from scratch again. Okay, here are my 5 channels. I've got my stress life glyph. Remember, we've talked a lot about the stress life methodology, SN here. That's the glyph you have here, this one here. And this one really um, 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 contains all the knowledge you need to be able to make fatigue calculation. So how do you, but this is not set in stone, right? You might want to have specific values of the B values. If you remember the slope, you might want to change things. How would you do that? You would just click on one of these glyphs here and change the properties, and then it's up to you to enter the right values. You can make your own settings so that the calculation we're making here really reflects what you have in your own case here. So it's very simple. You just click on the glyph and you're able, like this, and you're able to change a handful of parameters that allow you to customize the calculation so that it suits your need. And once we have done that, it is as simple as connecting the display viewer here, which I call fatigue result, and then I'm just running the flow. Okay, it's very quick. It's done here. And what do I have here? I'm just displaying for the 5 channels, number 90 to 94, their title, the units. So they were measuring micro depth. So that was for strain gauges. That's correct. And then I've decided to display the maximum, the minimum value for each of the strain gauges value here. What is the max? What is the minimum value? That could be useful for me as an engineer to investigate what's going on. And finally, what we are really after and what ENCODE Glyphworks calculates for you automatically. That is here the total damage here, the life in terms of repetition of the input signals. So here, these are the strain gauges recordings. And finally, I've decided to express that result, that fatigue result, in terms of hours. So here, how do I interpret this result? It means here that for the first strain gauge here, after roughly 1,500 hours, my component will break. I have this amount of life available within my component given that loading, that given loading. And the same is done for each and every channel here. So for all these strain gauges recordings here, I've got 5 here. It's not difficult, 5 of them. I've got my life in hours. Very, very simple. And the good thing of that flow here is that I'm setting it, I'm calling stress, life, fatigue, and this I can just share to my colleagues. And now everyone, my colleague from the test measurement, tomorrow can open up their ENCODE software, just load this input file here into their input with new measurements they will be doing tomorrow, and have this readily available without doing anything else. So very simple reuse, and that's one of the great strengths of the flows. Once they are created, they can be very easily be reused by anyone in the company, and you can even log them. You can make sure everyone does the calculation in the same fashion. So it allows for traceability and making sure everyone does things as they should be done. All right, so let me switch back into the PowerPoint presentation. We have covered the stress life method. Now let's look at the second route, which is the strain life method. So sometimes, in short, EN methodology. Just as we said for the stress life method, the same applies to the same holds for the strain life method. the similitude principle is still valid. So what was true for stress remains true for deformation values here, meaning we can there is a symmetry between the strain between the component and between the test coupon. The 5-box trick we have remains the same, so that's same. This still applies. So there is not much change here. The thing that will be changing, because we're using the strain life method now, strain here, the thing that will be changing will be typically the curve. Remember before we used the SN curve for the stress life method. Now we're going to use another kind of curve, which is really dedicated for strain life calculation. So this curve is a bit different than the one we've seen before. It's a bit more involved. Let's see all together how you would characterize your material for having the strain life methodology in mind. So first off, what does stress describe? Well, it really indicates to us how much we are pushing or pulling away the planes in our material. That's useful and that's good to know. However, what the real driver really from the physics point of view, the real driver to fatigue is the strain deformation, how my molecules will move apart one from another within the component, within the item. So strain really is the main driver. The thing is that strain and stresses are linearly related, as we say here, only under purely elastic. And the big word here, the key word is elastic conditions. So as soon as there is non-linearity, the relationship between stress and strain is no longer linear, and we have to be very cautious here. And that's the reason for us saying earlier that the SN methodology is not applicable to low cycle fatigue because of this linearity and the elasticity conditions not fulfilled in real life. So when you will have plasticity, typically SN will not be applicable, whereas EN works. In short, in a nutshell, the EN methodology works in any case, both for the low and the high cycle fatigue. So simply said, if you want to be on the safe side, if you have your material characterized for the EN methodology, it's very fair, very fine to use the EN methodology. It always works. It's always fine. Now you will ask me, then why aren't all people using EN, right? Well, the thing is that, as you probably guess, characterizing the material in terms of EN is more tricky. It requires more knowledge, more time, it's more advanced, and sometimes you're just missing this material characterization, and that's why not having such material characterization, people are left with the SN methodology. That's the main reason. But if you have all the material characterized for the EN methodology, then it's totally fine to use it because it works in any case. So I said it was more challenging to characterize the material in strain life or strain life. There are some regulations. We have a lab within HBK that been doing this kind of testing for many years. People are very knowledgeable, very really high experts in this field, because this is really tricky. Again, if you're not from that field, it's very easy to make mistakes. We can do that for you. We have a lab that allows to characterize your coupon, your materials in terms of fatigue. You need. I'm not an expert in that, really. My colleagues really. If you have questions, I will forward your questions to my colleagues that are really expert in this kind of testing. And again, if you have the need, if you want to characterize your component because you're missing this low characterization, feel free to reach out to us. We will be very happy to have discussions with you. So you need to do that. You need high quality test specimen, polished surface, and you will this time monitor the variation there is within your structure in terms of strain. So you will not record the stress values, but you will monitor how the strain is varying within the material. And typically when the strain will drop from 20%, when there will be a 20% drop in the strain values, you can safely assume there has been breakage, and this is the number of cycles that lead to breakage. So the difference again between stress life and strain life characterization is that now we are using really strain rather than stress to identify the number of cycles that lead to failure, and that apparatus is more involved. It's more advanced in terms of testing measurements. So really have this test be done by expert people. Otherwise, you might have input data that's not of high quality, and if that input data is wrong, the whole fatigue calculation will be off by an order of magnitude. Okay. And yes, last point here, important one. In wheel components, when you have small notches, you will create localized yielding. There will be plasticity, and you really have to take that into account. Another important thing to mention here is that why do we focus so much about plasticity? Why is it important? First off, strain life really, as we said, tracks plasticity, and as such will account for residual stresses. What are the residual stresses? You might not be very familiar with this. These are the stresses that remain within your materials once you've removed the loading. This could be due to manufacturing processes, short pinning. Well, there are a couple of different processes that could result in residual stresses in your component. Strain life takes that into account, whereas again, stress life uses a purely elastic material model, and as a consequence, will not account for those residual stresses that you might have from your industrial forming process. So now let's have a look here on a strain evolution over time. To the left here, we see strain is up and then down here. And what we will typically do to understand what's happening is we will plot the stress strain in the stress diagram, in the stress strain plane. We will track the evolution of the stress versus the strain while being strain controlled. So everything is driven by the strain value here, and we will track down how stress and strains relate. So we have 2 points here that are of noticeable here. This one here is when you have no load here. This one here, no loading here. You still have some, because stress is 0, you still have some deformation, so under 0 load. So that will be one point to consider. And there is also this one here, which is the residual stress when there is no strain. So here you have stopped submitting your item to any loading, so there is no strain anymore. But you see that the stress value here has a given value which is not 0. So there is some residual stress here, and this must be taken into account. One thing I said many times already now, and I think everyone will get out of this seminar having this in mind, cyclic loading is one of the key in fatigue. And cyclic loading is characterized with what we call, it's a big word here, hysteresis loading, hysteresis curve, stress, strain. This curve that we have here will generate what is called an hysteresis loading curve. Hysteresis is a big word. I think it means it bears with memory and things like that. It's from Greek, of course. It's this, and you might have seen those before in the past here. What do we mean with hysteresis loops? It simply means that when we start loading and unloading the component here, we'll have such curves in the stress strain plane here. We have these loops here, and typically they are called hysteresis loading because the material has some memory. So the curve, after some stabilization initial phase, the curve will just repeat themselves here. You will have, after a couple of cycles, you need a couple of cycles for that to happen, but after a while, the curves really stabilize, and the hysteresis loops manifest itself very clearly, such as this one here. So you do that. You load and you drive and you measure the strain values, and you depict the curve, the relationship there is between stress and strain in that form here. And why? And that's the reason why the EM methodology is much more complete than the stress methodology. It is more complete because the plasticity part, the one you see here, the small epsilon epsilon stands for deformation. This plastic deformation is there on the stress strain curve here. So not only do you have the elastic deformation that you have with the stress approach, but you also have, in addition, the plasticity value here. And these two added together gives us the total strain value here. So this strain value is really the sum of the plastic part, the one we have in the elastical linear domain, elastic domain, and sum with the elastic one. So plastic and elastic sum up together to form the total deformation. And that's a stronger set of the EN approach. Okay, so this is again an illustration of the fact that after a couple of cycles, the hysteresis loop will be repeatable, and you will have it such as this one here, depicting the stress value with the total value of deformation. And here, this is what happens when testing. When we say testing is over, we have the number of cycles to consider when the load in terms of deformation is dropping typically by 20% or so. Again, for more details on this, if you're curious and if you need material characterization, get in touch with me, and my expert colleagues in the lab will be very happy to engage discussions with you. Okay, here we have some examples of doing this testing for various test samples here. And in the end, after, it's just like with the stress approach, we test many samples, and testing many different samples, submitting them to different loading control, different strain control, will allow us to get a curve that depicts the global behavior of item, this time not in terms of stress, but rather in terms of deformation. And we reach such a curve. This is really the counterpart of the S and the Voller curve here for the EM approach, the strain life approach here. So we think that this curve here is more complicated. That's why I said that sometimes you might not have this curve if it's not been characterized earlier, because it's more complicated to get also. So we have the very well-known, this formula here on top might look familiar to you now. It resembles very much to one we've seen before for the stress life approach. The new thing here is that, so this curve here, the elastic is the blue line here, you see. The new thing is that now we, in addition, have the plastic lifeline. That's the one here. So with new coefficients and new slope coefficients also. You see this is the slope of the plastic life curve here. And then the total life will be the summation of these two lines here. So the total life strain life curve is the one that you see in red here. And this is, again, just to make it very clear, this is why SN doesn't work well here, because SN is really the blue line, as you see here. Whereas when we have plasticity, as soon as plasticity starts being involved, we've got the green line here that makes for most of the that makes for most of the total life in the strain life approach. And the green line here really results from plasticity, which we don't have in SN. That explains why, if you want to model your fatigue calculations, including plasticity, you must revolve towards the strain life approach. And the curve, how do we get this curve here? This curve is called the cyclic stress strain curve. Well, simply enough, we will have many of these hysteresis loops for many of the points, many of the testing points here. We will simply take the point or the tip of this hysteresis loop here, and we just join these dots here. And this is how we reach to the so-called cyclic stress strain curve. Remember, fatigue is always concerned with cyclic phenomena. There's repetition here, and we have the so-called cyclic stress strain curve, the one you see here. And the equation is I think it's called the Romberg-Osgood, if I'm not wrong. Well, this is the equation we have here. It's a relationship that relates strain to stress. This one, you're very familiar with this one. I'm sure the first part is something we learned all in high school, I think. It's the Hooke's law here. And this one is the new part that is brought by including the plasticity term. And this one is new to the curve here and makes it possible to include plasticity in the calculation. So all in all, this equation here relates deformation to stress involving plasticity. So this is the full equation, the cyclic strength, and this is, on the bottom here, we've got the cyclic strength strain curve, and on top here, we've got the strain life equation. These are the various parameters you need. I'm not going to go over them in detail. You see there is more than one. That's why it's more complicated to measure and to get to these strain life parameters in testing. And that's why you need expert people to do that for you. Okay, what about stress concentrations and notches? We have addressed those before, and this slide here is you probably recall it. We've seen it before. Now we're addressing the same challenge here to address these stress concentrations, but this time in terms of the EM methodology. So what is at stake here? How do we do that? What we measure really in real life will be the strain, but it will not be in the hotspot. And the hotspot really are the place where it's difficult to locate our strain gauge, because there is some curvature, a radius that might be a little sharp here. So practically speaking, it will be very difficult to instrument and to place the gauge here. But however, this having the right value of strain will be vital here, because otherwise we make wrong calculations. So we must find a way to move from the nominal strain value, strains and stresses value, to the hotspot, the high values in such places. And a way to do that will be to use a tool that's called the Neuber's rule. In case you have not heard of that before, the principle is rather simple. Neuber's rule say that it's an energy equivalence. So we are just looking at energy in our stress strain curves here, and we're going to say that we can do the calculation during the things as if the material were behaving in a totally elastic manner, and that's the blue line here. So we make our calculation having a simple linear finite element analysis typically, and we said that we want to make use of the elastic plastic material response curve. And what Neuber says is that when we calculate the energy contained from the linear elastic calculation, that's the blue rectangle you see here, well, this energy will be the same as the one you would have if you would take into account the elastic plastic material response. So here, this dotted yellow line here is called the Neuber hyperbola. It allows you to move from things that were calculated with only a purely linear hypothesis, and to switch and to move really to the stress and the strains as locally calculated, including the effect of the hotspot values. So in a nutshell, the goal here is that you make your life simple, calculating things as things were linear, and then you will use this simple Neuber's rule to take into account for the plasticity that really exists when yielding occurs. And in turn, you will make calculation having the local responses here that include these plasticity terms. So your calculations will be accurate. It's simply that you've made your life simple calculating things linearly. Of course, there are some assumptions about that. You cannot always do that, but it's a very well known and very much used tool to jump and to reach and to calculate hotspot values from a linear elastic, purely linear elastic calculation. Okay, so we talked about earlier about Neuber's rules. This is what is expressed here. You will do your loading, your unloading, and using Neuber, you will use the cyclic stress strain curve that we described before. It was obtained through the hysteresis loops. And using this Neuber hyperbola, you will be able to track the evolution of strain over time, including, and that's the important thing here, including the hotspot responses. In summary, for the strain life method here, we've seen what it is. It's a methodology that relates now the number of cycles to failure to the strain, the deformation value. So strain cycles to fatigue. That's the strain life method. And we call it in short the EN curve. It's valid in, it's always valid. It's like in whatever the fatigue regime, low fatigue, high value, high fatigue value, values from the number of cycles, it works fine in all these cases. So it always works. And that's the great thing about the strain life method. It always works. And the nice thing is that it takes into account plasticity, and it's very, very fair to use it even after yielding, which was not the case with the stress life. So it's more general. It's much more general than the stress life. It's more involved in terms of material parameters. You need to have such curves graphically characterized. That's why you need to have this data set of material available. Otherwise, and probably done by expert people. Otherwise, you don't have access to these curves. Okay, and again, there is an effect of mean stress, and this mean stress effect also holds for the strain life method. There are ways to correct for that. I'm not going to talk about in details about that today, but know that rest assured that in our software there are tools and there are ways to take the effect of mean stress into account, whatever the methodology you choose to make your fatigue life calculations. Numbers being one of them, but there are other stress corrections available in our software. So time is really flying, and let me speed up a little bit. Strengths and weaknesses of the EN methodology. The strengths, and I really want to focus today on those really. The strengths are that it accounts for localized plasticity, and as such, it's always valid. So you can use it in any case. It will be good for estimating both short and long life. So EN, the great point of EN is that it always works fine. What are the drawbacks or the weaknesses? Rather, by hand, it's relatively complicated. I think it's even almost impossible. It's so cumbersome. By hand, I think you are taking a very difficult path if you want to do that without a software. Welds are more difficult to model. Well, welds, I think they deserve a seminar per se, really, because welds are another kind of failures, of reason for failures. So let's not talk about welds so far today, but welds are really necessity specific approaches. And the applications of the EN approach is you can use it in high and low cycle fatigue, whatever the kind of folding you have, it works very fine. So again, on the fatigue loading, we have seen before these kinds of loading. I've explained Minor's rules, and now let's focus really on the variable amplitude loading, the one you have here. The goal is to have some cycles, right? But here it's very difficult to see the cycles. It doesn't make sense. Which are the cycles here? When we just look graphically at this recording from the measurement, our measurement colleagues here, we don't see any cycles. So how can we find out the cycles contained within that signal? Really, I'm repeating myself here, but really we need the SN and the EN curve are really done with constant amplitude loading in mind. So while or when your loading is not such, you have to find a way to find the cycles. So how do we do this? We do this using the rather well-known rain-flow cycle counting. Rain-flow is a keyword here. If you are interested in fatigue and if you want to look in more theory about fatigue, you will see that very quickly. Rain flow. This is the established manner to break down our signals into a number of cycles, loadings, values, and number of cycles. So it is standardized. There are some. The algorithm is very well defined. It's there. If you're curious about knowing what it is about, have a look at this standard here, and it allows us to break down our complicated signal, something that could look such as this one here, something that's not easily tractable when we want to make the calculation, into something with which we can use the EN or SN curve that were done for constant amplitude loading. So that's the outcome here of the rain flow calculation. It's good. It's very common practice to represent the result in terms of a histogram. So this is an histogram view done in ENCODE here that shows It could be for that signal here. What have we done here? This signal that we see here, this signal, we'll break it into different ranges and mean values, and we will count. So we'll count how many cycles there are that have, let me zoom a little here. We will count how many cycles have a low range value at this range value here, and simultaneously we will keep track of the mean value. Remember, the first parameter that affects fatigue is range, but mean plays a role here, so we will track both, and we will display then the number of cycles contained within the signals we see here, and that's good. We have a big number of cycles, but they have very low range here, very low range value, and that's good because this is not very much damaging here. And then we see how many cycles there are at various ranges here and various means here. So this is the rain flow counting algorithm. And then we just do the same thing as we did previously. We will be able to calculate life for all these bars here because we have a number of cycles here. And this is really what we needed to apply the Miner's rule and to calculate the damage through the strain life curve. Now we're using strain life. So just as before, we're looking at the curve to find out the number of cycles allowable, permissible before failure. And we will report that number to the number of cycles that we have found thanks to the rain flow algorithm. So this number of cycles here, this one here, will be used in just the same way as we did before. And then we can calculate our total damage when the amplitude is varying over time. And the same rule of accumulation of damage through minor holds true. So to conclude here, most measured loads or stresses are highly variable, and we have to find a way to approach and to find the number of cycles. And the tool used for that is the rain flow cycle counting. It's a very effective way to break down your signals into small cycles from which you can calculate fatigue using the tools and the rules we've seen before, typically the Miner's rules for fatigue calculation. Rain flow and minor, they really go well together so that you can calculate your fatigue both in terms of stress or strain life method. Both ways are approachable. Some application and some examples finally to conclude the seminar before the Q&A session. The methods, we have talked mainly about stress life and strain life. Okay, that are the core methodologies. Now, when you have more specific needs, and typically when you're dealing with multi-axiality, which is a rather complex topic in per se, on when you are doing vibration fatigue. Vibration fatigue is a very specific topic, but it's very important in real life. Fatigue due to vibration phenomena. You need to do things to analyze things specifically in the software. We have got the tools to do that really very efficiently. While fatigue, as I said, is very specific, and we have got dedicated glyphs. Remember these boxes? We have them available for addressing welds also. And we also have data and techniques for addressing high temperature fatigue and crack growth. And remember here, with these pictures here, how dramatic fatigue failures could be in real life. So that's why, as I said, starting the seminar today, addressing fatigue is really important when you have to deal with mechanical components. Okay, two routes in the software. The GlyphWorks route, and the GlyphWorks route simply means we're going to use measurement data, measured stress or strains. That's GlyphWorks. So you have strain gauges here that you place on your items, you get measurements, and you want to calculate fatigue. And we can also use finite element modeling, and that's design life within ENCODE. Design life will allow you to leverage your calculation, your 3D calculation, to make things before having any prototype available. So that's very powerful. So strain gauge concept here, we will use strain gauges to predict fatigue life in critical locations. It's simple, it's well adopted historically, it's been used for years, and the strain gauges can address nonlinear thermal issues very well. Now the thing, some of the cons, drawbacks or weaknesses of the strain gauges is that you will need to redo the measurements each and every time. Contrary to design life or to numerical calculation, when you have a physical prototype, every time you change the design, you need to have a new campaign test measurement. So that's a bit time consuming, and that's not ideal. But Still, it remains very useful. I'm not saying it's not useful. It's only you need a physical prototype available. So let's briefly, let me show you briefly or quickly in the software again. So let me switch to two software demonstration, one with Cliffworks, a full demonstration. I have prepared that beforehand so that we save time. Just same example as before. Here, the only thing, before I used a stress life glyph, if you remember, and now I'm using a strain life glyph. So for you as software users, it's not more complicated. We've seen that the strain life approach is more involved. There's more to it. But as software users, the difficulty is just the same. The difficulty has been baked into the strain life glyph. So Glyphworks allows you to use this recorded strain gauges measurements here. And from those here, we will be able to calculate the life, having the rain flow counting algorithm at play here to allow us to see the number of cycles just visually displayed here, and we can loop through the channels here. So for each and every strain gauge measured here, what is the number of cycles at the bottom here, here. And on top here, we have the calculated damage through everything we've explained during this seminar. Minor rules for damage accumulation done using a strain life curve. That's the result of the damage here for each and every channel here. And finally, we can display the damage as we've done before with a simple display here to express the total damage in having done the calculation through the very generic, always true strain life approach. And finally here, we've also superimposed the strain gauge result measurements. So that's the one you see in red here on top. And at the bottom, we've got the damage that's due to these measurements here. So we can clearly see the sections in the signals that are responsible for damage here. That allows us to do many things. That could be, we could say many things about this. This could be a way to reduce our time signal to have the test done faster, right? Because if we would just play the blue sections here, we would really play what's damaging for the component, but in a much faster way, because they are these are present during a short amount of time. So this opens up the way for techniques such as accelerated testing, and this is a methodology also available within ENCODE, the ENCODE software. All right, back on the software, the PowerPoint material here. To conclude, let me just show you an example of finite element based calculation with Glyphworks here. The concept is that we have made the calculation with our a structural analysis software, such as it could be Abacus, ANSYS, Hypermesh. Choose your favorite software for making structural calculation. We do that beforehand, and then we use that calculation as an input for design life. The great thing here, the great advantage here is that we don't need any prototype at all. We do everything virtually here. So it's a very quick way to assess for design changes. It's very easy to modify the radius here, to change the thickness, to have a new mesh, a new calculation. Just in a day or two, you do that, and you have your new result in terms of fatigue calculated very, very quickly without needing to instrument with strain gauges that might take quite some time. And in the software, in design life, again, within ENCODE, it is design life that addresses numerical calculation. We have various solutions, FE solutions supported. We can address dynamic calculations, linear, of course, frequency response solvers or handle. There is a lot you can do within design life. Okay. Fine. So just to conclude, let me switch back to design life here. This is my design here. So this is a tool here in the viewer. It's been calculated beforehand. I can zoom in, zoom out. Well, I could also display the results there. And what do I bring here? I bring my real-time measurement. So this is a loading that's been measured really, and my physical that's been instrumented really. So I'm using, and remember, this is what I said. You really need your end user real loading to make calculations that are truly and widely applicable. So here, this is the load that really characterizes our end user, and we are using that into design life. So we are really using numerical calculation and physically and real world measurements. We bring that into this EN analysis glyph, and this does all the job for us, this glyph here. It will calculate everything for us. And then we just run the flow here. Okay, it takes a little time here to finish up the calculation, and then we have the result in terms of fatigue on our control arm here, with the life in repetitions on the input signal. Okay, so I'm a bit late on schedule, I believe. So let me just move here. And we have in Design Life, we have the principle of stress superposition. So you can combine here. I had one loading in that example I just showed you, but you're not limited to that. You could have various loadings and you could combine them all within Design Life in a very straightforward manner to calculate your fatigue, having different load cases. In summary, I'm not going to go through this table here. It's more for you as a reference when you look at this later on. The differences between the stress life, the strain life approach, the pros and cons of each of those. Craig was also on the last column here. And what did we cover? We have, I think, covered quite a lot of things during the 3 hours today. We introduced fatigue, highlighting how important it is in real life. We've shown an overview of fatigue analysis. We talked about the two main routes, stress life, strain life. And finally, I showcased to you some examples using our software, Encode, GlyphWorks, and Design Life, both for strain gauges and for using finite element calculation. That was the purpose of that seminar, not to draw you into calculations, mathematical formulations, but really to highlight the principles behind fatigue calculation and to show you really how you can do that in our software in a very effective manner. This is what we learned, the fatigue, what it is, the physics behind it, and what drives fatigue, stress and strains, and all the details. Okay, so that was all on my side. I'm a bit late on schedule. I think Laila wants to introduce some coming webinars now.
Yes, thank you a lot, Nicolas, for this really interesting webinar of 3 hours. We have had a lot of questions in the Q&A and in the chat, and I would like also to thank Nicolas Seas in the background who answered really quickly and directly to everyone who asked any questions. Just before moving into the Q&A portion, meaning the question that have not maybe been answered yet, I would like to share some information concerning HBK activities. And just as a reminder, this webinar has been recorded and it will be available within the next 24 hours on hbkworld.com. You will receive an email, a thank you email with a direct link if you want to review it. So, as you might know, the ReliaSoft and Encode website recently moved to hbkworld.com that you can see on the screen. So this will bring together HBM, Jewel and Care, Encode, ReliaSoft, and Discoms brand all together, helping you innovate faster for cleaner, healthier, and more productive world. So I just invite you to go onto this website and to see how it looks like. Just as for information, you can see on the top how to find the encode and reliability software project. So you will go into project, you will find solution there. Thank you. Then you will have durability, and then you will be able to select the solution that has been shared today. In terms of the training, you might also know that we have an online academy, and many of you are already familiar with the training program. So here is a list of the upcoming training courses, and you will find the full list on HBK online courses at HBK Academy. Concerning the upcoming webinars, so we will have 3 other digital seminars, meaning 3 hours free webinars in the next coming months, in June for design and reliability, in July for improving durability and reliability for electrical vehicles, and one in October for the RAM analysis. We will also have within the next week a webinar on the 4th of May concerning durability of modern engineering material and structure. You will also receive an email concerning this webinar as an invite if you want to get to know more about it. And in August, you will have standardized base reliability prediction with Lambda Predict. You will be also able to see all the list of the webinars also on hbkworld.com at Academy Webinars. Well, thank you a lot for all your question. I will let Nicolas Sias and Nicolas Baron just review if we have some question to answer. And thank you a lot. Nicolas, I'll let
Yes.
you go through
Yeah.
the question maybe.
I'm sorry I'm a bit late, so there's little time for the questions, but let me quickly skim through them. I think are there any questions unanswered? I see that Nicholas has answered too many of them. Why don't we? Okay. Someone is asking, why don't we use nonlinear FEA directly? Well, you could. That's no problem. You can do that. It's just that it's more involved, and you have to be really knowledgeable in what you're doing in terms of structural calculation if you want to have nonlinear calculation. But you can definitely if there is a formulation of your material nonlinear or for big high deformation, large displacement, that's okay. So you're not constrained to do linear calculation with the software. You can do any kind of calculation you want in your software and bring that into Design Lab. That's no problem. What we highlighted with numbers, it was just a way to simplify your life. If that is valid, do the calculation simply linearly and then take into account non-linearity using some corrective tools. That's the only thing. Okay. Can we do fatigue for plastic materials? Yes, you can. No limitation in theory. The hardest thing for plastics, however, will be the curve characterization, the strain life curves that we talked so much today extensively. They are usually harder for plastics, so that will be the one of the main limitations. But in theory, there is nothing preventing you from doing calculations with plastic parts, even if, as I said, in real life it might be a bit harder. Let me see. Nicolas answered. How is your suggestion continuing fatigue factors for sheet metal casting forging? Well, okay, a very general question here. In the software, we have tools to correct for the way that the process involved in creating the material, whether it is sheet metal casting forging, you can modify the SN curve to take that into account. So in the software, there are ways to account for the ways, different process ways to create your items. Is it possible to use strain life method for welds? Yeah, sure. There are strain life curves for welds. Yeah, sure. Well, welds are, it's always a topic of interest. Welds deserves another seminar or a webinar, and there are many of webinars already registered on our website regarding welding techniques. Have a look at them if you're interested. Really go on our website, and you will see there's a lot for welding approaches. It deserves an entire webinar. So I'm not going to answer in 1 minute here, but we definitely can do weld fatigue in Design or in ENCODE in general. And we are over time, so let me see if some questions are left here. I think, well, okay, we're over time, so I'm going to have a look at all this after the seminar, and if some questions have not been answered, I'll do my best and try and answer them as soon as possible directly to the people who have asked these questions.
Yes, thank you a lot, Nicola. Maybe if you can share just your last slide with all your contact information in case someone would like to contact you directly.
Sure.
So there appears Nicolas'
Yes.
information, both Nicolas, right?
Yeah.
So please do not hesitate to contact them by email. You also have the phone numbers if you want to contact directly.
Yes.
So as I mentioned, the recording of this webinar will be available for viewing and sharing in 24 hours. I would like again to thank you all the attendees and thank both Nicolas, so Nicolas Baron, Nicolas Sias. So this is the end of the webinar and hopefully to see you for the next one. Have a nice day.
Bye.